Okay, so complex numbers, I is equal to the root of minus 1, I squared is equal to minus 1. So if you have the root of a minus number, you can split it up into the root of the number by the root of minus 1. And then you get the root of 4, which is 2, the root of minus 1 gets substituted by I. So that's your imaginary part of your complex numbers, because your complex numbers are made up of a real part and an imaginary part. So we normally call complex numbers z's. So z is equal to a plus bi, where a is your real number and bi is your imaginary number. Okay, so if we wanted to solve this, for example, it should just be x squared equals minus 25, x equals the root of minus 25. We split it up into the root of 25 and the root of minus 1. The root of 25 is 5 and the root of minus 1 is I. And you're done. Here, it's a quadratic, and when you start to look at it, you see, could you factorize it? And then you figure out, no, I don't seem to be able to factorize it myself, so let's use the minus b formula. So a is equal to 1, b is equal to 2, and c is equal to 2. So your minus b formula, minus b plus or minus b root of b squared minus 4ac all over 2a. So filling everything in. And then, so if you put it into your calculator like that and you get an error, it's probably because there's a minus under the square root and your calculator doesn't know what to do with it, but you know what to do with it now. So just do what's under the root and find out what's the answer. So minus 4 is under there. So then that becomes minus 2 plus or minus the root of 4 by the root of minus 1 over 2, which is minus 2 plus or minus 2i over 2, which is 1 plus or minus 1i, because you can divide them both by 2. Does that make sense? Yep. So the root of minus 1, that's the imaginary bit, yeah. So if you had tried to put this into your calculator, it would have given you an error. So if ever you're doing minus b and it gives you an error, it means that there's a minus under the root. And just do the bit under the square root yourself and figure out what the number is, and then you'll be able to apply complex numbers. Okay? So then when we're adding and subtracting complex numbers, we just add the real parts to the real parts and imaginary parts to imaginary parts. So I'm not going to do any adding and subtracting. I'll do a multiplying. Alright? We'll be adding and subtracting within that. So when we multiply two complex numbers by each other, it's like in algebra when we have two brackets multiplied by each other. We have to multiply everything in the first bracket by everything in the second. So we write down the first term from the first bracket with the second bracket, and the second term from the first bracket with the second bracket. And then we multiply. 3 by 4 is 12. 3 by minus 3 is minus 9i. 5i by 4 is plus 20i. And then 5 by minus 3 is minus 15. And I by I is I squared. Now, from back up here, I squared is equal to minus 1. Okay? So we never end up with an I squared in our answer. If we have an I squared, we should be replacing it by minus 1. I can put my two i's together. I have minus 9i plus 20i. So I have plus 11i. And this becomes minus 1. So minus 15 by minus 1 is plus 15. So 12 plus 15 is 27. Plus 11i. And there's your answer. Okay. So when we're adding there, we put the reals with the reals, the imaginary with the imaginary, and it's just like adding like terms in algebra. Any questions? Okay, so then we're going to do dividing complex numbers. So how we divide complex numbers is we want to simplify it really, and if it's a complex number under the line, then we want to turn it into a rational number, which is a real number, all right, as opposed to a complex number. And how we do that is we multiply above and below the line by the conjugate of what's under the line, because I don't know if you remember, but if you multiply a complex number by its conjugate, and its conjugate means that you're changing the sign in between the real and the imaginary part. So in this one we're going to multiply above and below by 2 plus 5i. Because you're multiplying opposite signs, the i's will cancel out in the middle because you'll have a plus and a minus of the same number. Okay, so whenever you multiply anything by its conjugate, the middle terms will cancel out. So you'll see what I mean as I do it. So we're going to multiply above and below by the conjugate of what's under the line. And we're allowed to do this because multiplying anything above and below by the same thing is just multiplying by 1. Because if you just multiply by 2 over 2, 2 over 2 is 1. Alright? So we're just multiplying by 1, so we're not changing it really. So then it's just multiplying after that. Take off the top part and multiply it out, like we did above. So then again, the I squared becomes a minus 1. So we have minus 14 plus 23i on top. And then on the bottom, minus. So here you have a plus 10i and a minus 10i, so they're gone. And remember, your I squared gets replaced by minus 1. So that's 4 plus 25, which is 29. So this then becomes minus 14 plus 23i all over 29. Now if it asked you for it in the form a plus bi, which it does here, split it up into two separate things. So it's minus 4 over 29 plus 23 over 29i. Okay. Okay. So it's just multiplying, but whenever you multiply a complex number by its conjugate, and its conjugate means you change the sign in between. Now make sure you have your real first and your imaginary first, because it is the sign in front of the imaginary bit that we're changing. When you multiply it out, your i's will go away, and because you have an I squared, you can change that to a minus 1. Alright?
There's a minus before the 2. Minus
here?
2, minus 5, yeah.
No, it'll still be minus 2 plus 5. Okay, so it's just the sign in front of the imaginary part. Alright? Okay. What's next? Okay, so if two complex numbers are equal, then their real bits are equal and their imaginary bits are equal. Okay, so here we have find x and y if this is equal to 8 minus 13i. So multiply out this side, put all the real bits together. So the real bits, although they're in terms of x's and y's and numbers, the real bits are the bits that don't have I with them. So we have x plus 2 plus 6 minus 10yi equals 8 minus 13i. So none of these have, oh sorry, that had an I. This doesn't have an I, this doesn't have an I. And that's it. So x plus 6 plus 2i minus 10yi equals 8 minus 13i. So now this doesn't have I and that doesn't have I. So x plus 6 equals 8. So x equals 8 minus 6. So x is equal to 2. And then 10i minus 10yi is equal to minus 13i. So then you can drop the i's. So minus 10y equals minus 13 minus 2. Minus 10y equals minus 15. So y equals minus 15 over minus 10. So y is equal to 1.5. Okay.
Did you just get rid of the i's in the second one?
Yeah, so they all have an I, so you can divide across by I. Okay. Okay. So then we're on to our Argand diagram, which is just your axis for complex numbers. This is your real axis and this is your imaginary axis. You don't have to put the i's on here once you call it imaginary, but it's not wrong to do it. So if I wanted to put 4 plus 3i is 4 on the real, 3i on the imaginary, and there's your complex number 4 plus 3i. The modulus of a complex number then, which is represented by this sign, so we've seen that before when we do length of a line, so it means length of the complex number, and what it means is length from 0, 0. Alright, so what they're talking about is this distance here. Okay, and how we get it is it's the number, the real number squared, plus it's only the number with the I. Not, do you remember when we talk about complex numbers, we say a plus bi. So this is 4 plus 3i. So a is 4 and b is 3. Don't put the I in, okay? Because that's where some people go wrong with getting modulus. So find the modulus of 4 plus 3i. So the modulus is the root of 4 squared plus 3 squared. So root 25, which is 5. So what you're saying there is that the distance from 0, 0 to that complex number is 5.
Miss, does it make a difference if you put the complex numbers on the horizontal axis and the other ones on the vertical?
Yeah.
Okay.
Okay. This has to be the real and this has to be the imaginary, yeah.
It's why did you put them both under the root?
So it's the formula.
Oh.
Okay, so modulus of a complex number, z is root of a squared plus b squared. Okay. You'll need it for writing them in polar form. Sometimes they'll just ask you for the modulus, or sometimes they'll say Z1, Z2 and Z3, find the modulus of Z1, find the modulus of Z2, find the modulus of Z1 plus Z2 inside the both together inside the modulus, and then they might say the modulus of Z1 plus the modulus of Z2 and see if they're the same thing. They kind of do them kind of questions as well. Okay, are we finished with that one? So then we're on to transformations when we have pictures in our Venn diagram and different complex numbers and doing different things with them. So what happens when we add, multiply, and so on. So Z1 is 4 plus 3i and Z2 is 2 plus 1i. So down here we're going to do Z1 plus Z2 and then we're going to stick it on the graph and see what happens. So Z1 is 4 plus 3i, Z2 is 2 plus 1i. So real with real, imaginary with imaginary. So I get 6 plus 4i. Okay, so if you look at at this complex number, and if you look at this complex number, for this one I'm coming out 2 and going up 1, for this one I'm coming out 4 and going up 3. So when I add them, it's just doing both of them together. So like there's nothing fancy about adding complex numbers, there's nothing really you need to know except that when I add 2 plus 1i to 4 plus 3i, I'm adding 2 to the reals and 1 to the imaginaries. Does that make sense? Yeah. I'm just going to call these different things now so we can. Two times Z1. So 2 times Z1. What's happening to each of my complex numbers? Each of my parts of my complex number, rather. It's just getting multiplied by 2. So 4 plus 3i is here. 8 plus 6i is out there. So you're moving it twice the distance from the origin. Let me update my. Okay, so the distance from here to here is half the distance from there to there. Alright, so this is being multiplied by 2. If it was being multiplied by 3, it should go 3 times the distance. If it's multiplied by half, what do you think? Half the distance, so it should be halfway here. It should be somewhere in here. Is that okay? So multiplying by a number. So moves it. Oh, so we have half, so let's just do it numerically. So a half Z1 so 2 plus 1.5i. So 2, 1.5i is here. So from there to there is half the distance from there to there. Now this is the next one is the one that is talked about most often. When we multiply a complex number by I, so we get 4i plus 3i squared. 3i squared is 3 times minus 1. So we get 4i minus 3. Now we always write our real part first and then our imaginary part. Okay? So minus 3 plus 4i is what happens when I multiply Z1 by I. Okay, so minus 3 plus 4i. Now I'm going to get rid of everything off the graph except z1 and no. So when we multiply a complex number by I, it gets rotated 90 degrees anti-clockwise. Okay? Okay. And then if I multiply that by I again, it'll go 90 this way. And if I multiply that one by 90, it'll go that way. Alright, and if I multiply that by 90, it'll get back to where I started with. Okay? What do you think would happen if I multiplied it by minus I? Yeah, exactly. So if it was minus I, it'd go this way. Perfect. Oh, I have it up here, so that's 5. So minus I times Z1. Okay, so 90 degrees clockwise. Alright, so 3 minus 4i. I won't put it on the graph because it might just confuse things. But if you can just keep clear in your head that multiplying by I does 90 degrees anti-clockwise, then everything else will... And you can do it anyway. And sometimes questions come up with an Argand diagram and they've just points and you're trying to figure out which is multiplying by which and what's being multiplied by I and everything. Give them, like, you can give it a scale yourself. Now your scale mightn't be exact, but it'll help you figure out what's going on. We'll look at some of them when we get to the exam questions. Is that all alright? Okay. Yep. The graph or down below. Number 5.
Could they show the questions, like they actually show the Argand diagram with like what's happening and then say...
They don't tend to, what they tend to do is give an Argand diagram with points on it called Z1, Z2, Z3, Z4 and you have to write down what's happening, what's the relationship between them. Or they've told you that they've just given dots and they told you Z1 plus Z2 equals Z3. I times Z1 equals Z4 and then you have to label the points. Yeah.
Could this come up as a long question or like...
No, complex numbers is a short question really. Now saying that everything can change, but all along it was always a short question. Okay, we good? Conjugate root theorem then is just all it's saying is that complex roots happen in pairs. So if you have a complex root, the conjugate of it will also be a root. Okay? So if z is a root of an equation, then z with a bar over it. So we never talked about that when we talked about conjugate. This means conjugate. Okay? So they happen in pairs. So if you have a quadratic and you know one complex root, then the conjugate is just the other one. If it's a cubic and you know one complex root, the conjugate is the other, and you'll have to find the third, which will be a real root, all right? Because they only happen in pairs. If it's power of 4, it could be two sets of complex numbers. So And remember from quadratics, any quadratic can be formed by doing, it used to be x squared minus sum of the roots, x plus product of the roots, but in complex numbers we call it z. Okay, so z squared minus sum of the roots, z plus product of the roots. Okay, so if z equals 1 plus 5i is a root of the equation, find a, b and c. So find the equation is really what it's saying. So from the conjugate root theorem, we know the other root is 1 minus 5i. Okay? So the conjugate of this, they told us this is a root, this is also a root because of the conjugate root theorem. And then we're going to use z squared minus sum of the roots, z plus product of the roots equal to 0. So the sum of the roots is 1 plus 5i plus 1 minus 5i. So the sum of the roots is 2. Product of the roots then so the middle terms are gone. I squared becomes minus 1, so 1 plus 25, which is 26. So then just filling it in, z squared minus sum of the roots, z plus the product of the roots. So a is 1, b is minus 2, and c is 26.
Should you always write it with the real number first before the complex number?
Yeah.
Okay. And like if you didn't do that, would you lose marks?
No, it's just for yourself, because everything we do to do with conjugate and graphing it, the real comes first and the imaginary is second. So it's just good practice to get into so that you don't make a mistake within the question. Z squared minus sum of the roots, no. Am I good? Still writing. Okay. Okay, so then just another example to do with conjugate root theorem. Given that z equal to 2 plus I is a root of that, show that z conjugate is also a root. So z conjugate is 2 minus I. So when we're showing something as a root of an equation in any sense, we can fill it in and it should equal 0. Alright, so instead of z, I'm going to put in 2 minus I here and multiply it all out. Now you could also do z squared minus sum of the roots plus product of the roots with the two roots and show that it gives that, that would also be fine. I just want to show you another way to do it. Okay, so I'm just going to change this to a -1. So we have 4 plus 5, which is 9, take away 9, so all my reals are gone, and then I have -4 plus 4, so 0 equals 0, therefore it's a root. Okay.
Is Z squared the same as Z1?
Pardon?
Was there already filled in?
Yeah, so they said given that Z is equal to 2 plus I is a root, show that Z with the dash, that means conjugate, alright, so is also a root. So we're saying this is a root, but you're just filling it in for Z, okay? So it's how we distinguish between the two roots, but it still goes in for Z. Yeah. Okay. Okay, so here's a cubic. So again, another example of this kind of thing. So given that Z is equal to 1 plus 2i is a root of this cubic, it's a power of 3. Show that the conjugate is also a root, and hence find the third root. So the conjugate is 1 minus 2i. So we're going to fill it in. It's just going to involve a little bit more multiplying out. So I'm gonna just oh, am I doing minus or plus? I just interchanged them there. Sorry, that should be a minus. Okay. So we need 1 minus 2i to be squared, and we need 1 minus 2i to be cubed. So let's do 1 minus 2i to be squared first, and then we can multiply it again. So it'll cover here and here. So 1. Now you can use your perfect square multiplying these out, but it's just with the I and the I squareds. Just be careful, alright? Okay, so when I multiply 1 minus 2i by 1 minus 2i, I get minus 3 minus 4i. Now keep an eye on me in case I make a mistake as well, because that could happen. So then I need to multiply that by 1 minus 2i again for the cubed one. So minus 3 plus 6i minus 4i plus 8i squared. Can you see what I'm doing? No, you can't. Sorry, I'm doing, what have I done there? So minus 3 plus 2 plus 8, right. This becomes minus 8 minus 11 plus 2i. Okay, so this is when it's multiplied together 3 times, so minus 11 plus 2i. I'm going to take it back up. And then this is when it's squared, so be careful, the minus is outside the whole bracket. And then 3 by 1 is 3, 6i plus 5. So minus 11 plus 2i plus 3 plus 4i plus 3 minus 6i plus 5. So then let's put the real bits together. So I have minus 11 plus 3 plus 3 plus 5. So that's minus 11 plus 11, which is gone. And I have plus 2 plus 4, which is 6, and take away 6. So I have 0 equal to 0, therefore it's a root. Okay. So it's a little bit of multiplying out. So if we want to find, if we have a cubic and we're given our root or 2 roots, how do we find the other root? Can you remember just from algebra?
Long division.
Long division, excellent. Yeah. So we have the 2 roots. So we have z is equal to 1 plus 2i and z is equal to 1 minus 2i. We can divide in by the quadratic. So let's make the quadratic. So z squared minus sum of the roots, z plus product of the roots, equals 0. So sum is equal to 1 plus 2i plus 1 minus 2i. So we're left with 2. Product, we've already worked out the product of 1. Oh no, we haven't, sorry. So 1 minus 4 times minus 1, so 1 plus 4, which is 5. Because my middle terms cancel each other out. Minus 1 plus 2. So my quadratic becomes this. And then I need to divide the cubic by that to get the last root. So z cubed minus z squared plus 3z plus 5. So z by z squared gives z cubed, by minus 2z gives minus 2z squared, and 5 by z is 5z. So draw a line and change your signs then. So that's gone. I have minus z squared plus 2z squared, so that's 1z squared. And I have 3z minus 5z, so minus 2z. And I'm bringing down the plus 5. So then what do I do to that to get that? It's just 1. So plus 1. So plus 1 by z squared would be z squared. Plus 1 by minus 2z would be minus 2z. And plus 1 by 5 would be plus 5. And you should end up with nothing when you cancel them out if you've done everything right. Okay? So z plus 1 is my other root. Alright? So z is equal to minus 1. So like when we're doing algebra, we have x is equal to, so here it's z is equal to. So my 3 roots are this, this, and this. So remember I was saying the complex numbers happen in pairs, and then your other one will be a real number. Okay. Let me just see what's next. We might take a break for 5 and come back. Yeah, pretty much. Okay. So we're going to do polar